As we discussed, one of the major reasons for DNS's vulnerabilities is the lack of authentication. The DNSSEC protocol adds authentication to DNS responses simply by adding signatures to the responses that are returned for each DNS reply. When a stub resolver issues a query, assuming there is no caching, the query is relayed by the recursive resolver to the root name server, which, as we know, sends a referral to .com, but this referral includes the signature by the root of the IP address and the public key of the .com server. As long as this resolver knows the public key corresponding to the root, it can check this signature, and it knows then that the referral is to the correct IP address for .com. It also now knows the public key corresponding to the .com server. Thus, when the .com server sends the next referral to google.com, that referral is signed by .com's private key. But the root has told the resolver the public key corresponding to .com, and thus the resolver can check that this referral is not bogus and in fact came from the .com server. Similarly, the .com server will return not only the IP address for google.com, but also the IP address and public key for the google.com authoritative name server, so that when Google returns its answers, the resolver can check the signatures coming from google.com. In other words, each authoritative name server in the DNS hierarchy returns not only the referral, as it would with regular DNS, but also a signature containing the IP address for that referral and the public key for the authoritative name server that corresponds to that referral. That public key then allows the resolver to check the signatures at the next lowest level of the hierarchy until we finally get to the answer.